Welcome anybody, thanks for coming. What I'm going to do today is I'm going to follow along a Dr. Milhouse video on C Structs, and I'm going to reproduce similar code using this compiler, and we're going to be able to compare the output assembly with the output assembly of a C compiler and see if we can learn something. See if I can learn something. This is my startup template I always use. All it is just a little console window program. Lets you press enter, the program ends. I'm going to start from this point. I'm going to run a function called main. I think I'm going to find it down here. And I think I'm going to split this into test 1 and test 2. Okay. I guess before I do all that, I need to make my structure. Let's see if I can pull up on my other screen. Okay. Mine aren't called structs, they're called types. Oops. I'm going to call it my type. And that's the syntax. Ignore the coloring that doesn't look good. We'll just pretend we don't see that. So my data types, I'm going to use assembly data types because I just think they're easier. Assembly data types are basically how many bytes. This is like a 1 byte data type. It doesn't really care what you write in there, just as long as it's 1 byte, which is a number between 0 and 255. And I'm going to put in there my letter. And what he calls my short, I think I'm going to put it as a 2 byte. Not sure if it's really 2 byte or not. So DW is 2 bytes, and my num, I'm going to make that a DQ, that's 8 bytes. A num. And I'm going to have another letter, 1 byte. Okay, so there's my type. Go down here to test 1. And what I'm going to do for test 1, and this won't be exactly like Dr. Milhouse's. This is easier for me to do it this way because I don't have a malloc, so for me to do malloc, it's going to be a little bit extra work for me. So what I'm going to do is I'm going to declare a local variable. It's of my type. And I'm going to name it my type. Now this word data here, you can kind of think of that as like static. It actually was static like 6 months ago, and I got rid of the keyword static because I felt like it was redundant. So data means that this variable will be part of the data block. And by the way, this type is in the data block, but it isn't really data by itself. It's just a definition. But this will be the first variable, or maybe only variable in the data block. And it's declared in a local function, which means it's just a thin layer of security that keeps it. This is the only function that's going to see this variable, but it's stored in the data block. If that makes any sense. Let's continue. So I like to throw no op in every once in a while to kind of separate declarations and function overhead, just so I can see where things start. I'm gonna say move my type dot. Okay, Okay, so my IntelliSense. By the way, this is all kind of new, and things may change. If you maybe watch other videos where it's not exactly the same anymore as it was 6 months ago. My type dot variables. Okay, there's our variables. We're going to do my letter. A. Variables dot my short. $255. My type dot variables dot my num. Feed beef. My type dot variables dot another letter. Be there. Okay. And this, like I said, this won't be really like Dr. Milhouse's example yet, but we're going to work up to it. Let's see if this compiles. Okay. Now, to run this, wouldn't show you anything because we're not printing anything, we're not echoing anything. This is so just running this doesn't help. So we're gonna have to go to the debugger. Okay, I'm here. I executed a couple lines. There's where the console window opens. I'm gonna drag that out of there. This would be, I believe this is our sub main call. That's our version 1 call. And there's our no op. Okay, so I don't know if you may notice or not, but there's not very much overhead on a function here. The only local variable is actually stored in the .data section. It's not on the stack, so there's really no lines of code there. Also, notice that 14140 in brackets is a memory address. I'm going to follow and dump 14140. So down here in our hex window is 14140. This debugger doesn't kind of show you where that number come from. It's actually the RIP register after this instruction executes, which is 12140, plus this number. And I believe that's 2000. Huh, what a coincidence. So there's your 14140, and it's actually in program space. And there's our 61 down there. We're going to put the 255 in. There's the 255. We're going to put feed beef in. Now notice that this goes into RSI first, and then into memory. That's actually kind of a long little discussion of why it does that. I'd kind of just rather not even go there. Let's just keep it simple here today. I did notice that the C compiler puts it into a 32-bit register first, and then puts the 64-bit version into the memory, which what that does is the upper 32 bits is going to be zeroed out automatically by the CPU, and that may be a little quicker than what I've got going on here because I've got extra zeros encoded in here, and they didn't. C doesn't, so that's kind of good. There's a learning. There's something learned. Oh, I'm way down there. So then there's 62, and there's 62. So there's our structure. There's our memory in program space, and there's our 1, 2, 3, 4, 5 lines of code that write the values in the memory. Fantastic. Let's go full speed. Press enter and done. Okay, so now what we really want to do was try to get some memory from the memory manager and write to that memory, because that's really what Dr. Milhouse did with malloc. And unfortunately, I don't have a quick one function call to do it, so this will be a little uglier. Let's make test 2. And let's invoke test 2. Okay, so first what I want to do is I want to make my type. Notice I kept the word date out of there, so this will not be static any longer. It's going to be on the stack. I'm going to purposely leave out a keyword here just to see if my error checker is going to catch this. So what I've done here is I'm going to try to put a type on the stack, and my compiler doesn't like that. So when I do the preview, it says, sorry, you cannot store data on the stack larger than 8 bytes. Try using the static keyword. Oh, the static keyword that no longer exists. Nice error message. Okay, don't use a static keyword because that doesn't work. I'll have to fix that message. So that's kind of one thing I got going on with this compiler is I'm not letting you put buffers on the stack, not letting you put objects on the stack, not letting you put types on the stack. And if I get my arm really twisted hard in the future, I may undo that. But for right now, it just seems to be working pretty well for me. So what we can do, what we can store on the stack is a pointer to my type, named my type. And the stack will let you do that because a pointer is 8 bytes. And pointers in the stack are fantastic. Plus, we're going to need a pointer anyway because we want the memory to be malloc from high memory. Well, we don't have malloc. Okay, so the next variable I'm going to do is this is going to be an object variable that is going to be in the data section. So that's, again, that means it's static. And the name of the object is called memory. I'm going to name it my memory. So what this is actually a class because it has instance data. And it's already going to be instantiated in the data block as a runtime object. So we don't have to kill it. We don't have to make it come to life. We don't have to kill it. It's just part of the runtime memory. It's just there. So I need a fancy line of code to do this. I'm going to say invoke my memory. And let's look for some function that's called code. And my memory is actually very simple. It's kind of new. It's very small actually. I'm going to do new from manager. Really what my memory is going to do for us is it's going to allow me to just type one line of code instead of like 3 or 4 lines of code. It's kind of a wrapper for using the memory manager is really what it is. And first thing I want is size requested. Okay, I'm going to do myType.size. Very small. Whatever myType.size is what we're going to request. Now, a description. This is kind of something my memory manager requires, is you to give a string description of and this is all kind of new, so I don't really know what to type here either, but I might just call test2 dot my type. We're not going to really be using that or looking at today, but it does require a description. And that's for a report that it creates of memory that isn't, released. Okay, so since my memory is an object, that somewhere in my memory is the address of the memory we just got. And I don't know if it's an REX or not. I'm not going to look at IRX and even tell because I guess I don't care. But let's now here's another kicker is that the my type variable is a pointer and it starts out as a null pointer. So now we need to assign the pointer to the memory that we just got. And IntelliSense has something called address pointed at. That's going to be the destination. The source is going to be my memory. We're going to look at the instance data, then my memory. It has a variable called reference. And reference is actually a pointer as well. We're going to get the address pointed at. So that's kind of a long line, but it kind of makes sense. You say, give me the address pointed at by this pointer and assign it to the other pointer. So now my type is actually pointing to the memory. Now we're going to go move my type dot. Now before we had variables, now we have variables at, because now it's a pointer. Let's go my letter, single quote, A. I need to do this faster. I'm kind of variables at dot my short, comma, 255, my type dot variables at my num, feed beef, my type dot variables at dot another letter B. Okay, now I'm not gonna clear the memory. Because I don't care. Let's compile this thing and see what we got. I see my preview still didn't clear the last error message. Little glitches here and there. Let's go look at the debugger. Okay. Let's see. Open main, console open, drag that out of the way. That should be submain. Let's just go into that. That's our first test. Look at that real quick. Go ahead and follow and dump. Boom, 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 boom. There, it filled up the values. Let's go to the second test. Okay. You don't want to stick a 0 there. Make sure that the variable is a null pointer. We're just going to jump over a little bit of text there. I believe it was our text, the buffer we typed in. We're going to load up CX and DX and R8. And we're going to go to the memory manager. I didn't step into that because it's kind of something that steps into something that steps into something. We don't want to trace through all that. So I think an REX here might be our memory. We'll find out in a second here. I'm gonna dump 2 is gonna have 1FD0120. Let's see, RSI. Oh, look, our magic number showed up again. Fantastic. And what did we just do there? I believe we just assigned the null pointer is now pointing to our upper memory. That's what those two lines were. And then we're going to load RSI with our value, our pointer, and we're going to move 61 into it. There's our 61 down in the dump. And we're going to load RSI again. Okay, so you see how it's just loaded RSI twice, and then the second one was redundant. And it's going to do it a third time as well, which is redundant. That's a compiler optimization that's not happening. It really only needs to do it once. So there, I admitted it. It's an optimization. It's not happening. I don't plan on fixing that anytime in the near future. I get too many other things I'm working on, so those little things don't bother me. So let's put 255 in RSI plus 1. Okay, and there it is. And that's the same as the C compiler, but notice feed beef goes into RDI this time, and it's plus 3. So the difference was the C++ compiler made it on an 8-byte alignment, and this compiler doesn't do anything with alignments. And I already knew that because I haven't made it do alignments, and until I run tests and prove that it actually makes a difference, I'm going to leave it the way it is. So there's a difference. And we're going to load RSI with the value it already has again. And we're going to go, the offset looks like a B. And there's our 62 way out there. I think it was a B. And there you go. The code actually, I believe, is similar to the C++ compiler with just a few variances. Let me just go take a quick look at it. I'll be right back. Okay, so yeah, it actually is very similar. I do notice that, you know, I already knew this, I guess, but I use RSP as my calculation of where I want to jump to and from on the stack. I don't use the RBP register. In most cases, I don't, unless I need to use it. And the compiler decides when and where, and it kind of reduces the overhead. There's top 2 lines at the top and the bottom 2 lines for epilogue and prologue. I skip through that. Again, the feed beef goes into a 32-byte or a 64-bit register, and the C compiler puts it into a 32-bit register. That's probably a little bit better maneuver that C did there. And we're both duplicating, loading the RSI, which I'm loading RSI, and they're loading REX. And there, yeah, it's kind of the same actually. That's kind of cool. Let's if you want to see this run out, press enter. Okay, let's go back and let's see what else we got. Well, Dr. Millhouse went into a union and kind of an array within the structure, and I'm not going to really do that because I'm not really built for it. So I think I'm just going to cut the video right here. Nice, short, sweet, and simple. Kind of a fun little project. Thank you, Doctor, and look forward to more in the future.